Hello and welcome to another exciting episode of Beyond the Bot, where we break down the latest in AI and robotics and what it means for you and your business. I'm Tony,
I'm Bhargav.
and we're in the Blue Sky Lab. Bhargav, you're a computer vision engineer on a day in, day out basis, right? So there's really nobody better to discuss these topics than someone like yourself.
That's correct.
So can you tell us, what does a computer vision engineer do actually on a day in, day out basis?
So a computer vision engineer builds computer vision algorithms, and in a general sense, computer vision is just a software technique of allowing computers to interpret, see, and understand the world around them. And these techniques can be very simple, from simple mathematical formulas, or as complex as AI or deep learning generative AI solutions.
So we often talk about computer vision from the frame of reference of artificial intelligence and machine learning, but it doesn't necessarily always have to be AI based to be computer vision. Is that correct?
That's correct. Yeah. So computer vision is typically regarded in relation to AI nowadays, but honestly, computer vision, even putting a filter on an image, is considered computer vision. So this just uses simple mathematic techniques. So putting a filter on an image or doing edge detection on images all even count as computer vision.
And when we say computer vision, sometimes that term can be just a little bit misleading, because when we think about vision, we think about, the way that our eyes see and perceive the world. But for a computer, it's not always like that. So, how do we translate, the shapes and colors and rich visual detail that we see in the world into, ones and zeros that a computer can understand?
So in order to do that, we have to leverage sensors. So sensors are a big part of computer vision. That's how we allow the computers to actually interpret the world around them. A very common sensor used is, well, just a simple camera, which is RGB, or a depth camera, which uses RGB and depth sensing technology.
Now, when we take something like an RGB feed from a camera, how does the computer actually understand that, sort of at a more granular level? Is it looking at the image as a whole, or is it, kind of processing pixel by pixel?
So it actually processes everything pixel by pixel. So unlike humans, where we can look at the world around us and just be like, oh, that's a mic, that's an iPad. A computer will have to take an image or a video and break it down into pixels, or like groups of pixels, and analyze how each pixel, its color and its value, relate to other pixels around them.
So, in more general terms, this is really sort of a statistical and pattern recognition process. Is
That's
that fair to
correct.
say?
Yes.
So, we have these sort of more basic algorithms that can do, sort of basic image processing. But how does AI and machine learning, expand the capabilities of those more basic pieces of software?
So AI and computer vision actually takes it to the next level. It's like the next step of autonomy, essentially. So right now, we have to program all these algorithms and all these statistical models for computers to kind of understand what the image is that they're looking at. But with the use of AI, we can actually just tell the computer, like, hey, this is what we want to see, or this is what we're interested in. Sometimes we don't even have to tell it anything, and it can kind of determine on its own, like, oh, this is what a cell phone looks like, or this is what an iPad looks like, or if there's multiple objects in an image, this is like what a cat generally looks like, and this is what a dog generally looks like, without us even explicitly telling it what a dog or a cat looks like.
Now, that's deep learning. Is that right? Can you help kind of clarify what is
Mhm.
deep learning? What is machine learning? How do all of these things kind of fit together?
Yeah, so deep learning is a subset of machine learning. Deep learning is commonly used in computer vision because we leverage what's called CNNs, or convolutional neural networks. A very common one that's used is called YOLO. YOLO is basically an object recognition neural network. So if you point a camera at, say, this table, it will tell you, like, oh, this is what, this is like two people, there's two mics. But there's also other models that leverage deep learning, such as ResNet, or some semantic or instance segmentation models, which, instead of just telling where the two people and the mics are, it will actually segment the image and separate the image of the people and the mics from the background and foreground.
So if we just take the YOLO model, for example, just to kind of have a starting point here. Now I know there's a lot of complicated math going on under the hood, but if we just sort of, simplify that training process or that learning process for that model, how does it know this is what a mic looks like, for example?
So that actually starts with us, the people. So we actually have to take multiple images or videos of the mic, from different angles, different lighting, and we use that as what's called training data. So we give this model, we feed it this training data, and it kind of learns through all the images that we took, and then it outputs what when we give it an image that it's never seen before, it will use that knowledge that it's previously learned to figure out, oh, this is what a mic kind of looks like from what I've learned, so this must be the mic, and give us like a probability.
So it's really kind of similar to the process of teaching humans a new skill. We show it to it, over and over and over again in different conditions, and over time, it's able to extrapolate out, sort of a theory of this is what a microphone looks like. And that's at the very granular pixel level, right? It's understanding, okay, this collection of black pixels relative to this collection of blue pixels relative to, this collection of background pixels leads to a mic. Is that correct?
That's correct. And actually, there's a more, you talked about how a human learns for machine learning. There's also an AI technique called reinforcement learning. So, reinforcement learning is kind of more like how, if you think of how a baby learns to walk, it's trial and error, right? So, a baby does not immediately know how to stand up and take steps. It has like the baby has to fail, like falls down, like it takes a lot of time for the baby to figure out what to do in order to actually successfully walk. So that's reinforcement learning is also used in computer vision, where we can give it a reward and punishment, and so we can tell it like, hey, when you see something that looks like a microphone, like that's a reward, like we want to reward that kind of behavior. And then if it says like this iPad is a microphone, then we punish that behavior to help. So in that way it kind of just learns on its own like what objects look like.
So in a YOLO based learning approach, we're doing kind of the human input on the front end and, sort of annotating that data, then feeding it to the machine to do, kind of complex pattern recognition based on that. But it sounds like for reinforcement learning, the human involvement is actually on the back end where we're, kind of monitoring this behavior in a simulated environment and saying thumbs up, thumbs down, good or bad job, basically. Is that correct?
Exactly. So it's kind of like starting from scratch. So
Wow.
you just point a camera at this table or anywhere you want, and then let it learn over time.
So certainly a lot of software considerations here, but I want to go back to one of the things that you mentioned earlier, which is the sensor piece of this and the hardware that's gathering all of this data to feed into these models. I suppose it's one thing to use an RGB camera to detect the objects in a frame, for example, but when we look at applications of computer vision in robotics or in other types of advanced technology, it seems like we want to know what something is, but also where it is. So how do we get that information?
Yeah, so an RGB sensor will give us basically the 2D information of where something is. In robotics, it's really useful to use LiDAR sensors or depth cameras. So a depth camera will leverage both the RGB sensor, but it'll also have a like a depth sensor. So the depth sensor is typically LiDAR, which uses laser light in order to determine how far away an object is, and in that way it can print out like a 3D map of its surroundings. So with that kind of information, we can combine all of that, and instead of just giving us the 2D coordinates of an object, it can give us the 3D coordinates of an object. So now the robot just doesn't know what something looks like, it knows where it is, and it can go and manipulate with it.
And not only does it know what it looks like, but it also sort of knows what it should look like in a lot of contexts as well, right? So we can do, it seems like the possibilities are kind of endless because you could do, kind of quality assurance and fault detection and feature segmentation and things like that.
Yeah, so combining that robotics with computer vision can give us a lot of power in these industries. So using computer vision techniques to do quality control of two objects and saying like, okay, the objects are good, they pass the test. Now the robot can also manipulate with the object, pick it up, and place it in a bin for packaging.
Wow, that's incredible. So, obviously this technology is very advanced at this point, but it seems like we're in sort of a renaissance for computer vision and robotics right now, where things are just growing and expanding and developing so quickly, it can be certainly hard to keep up. What are some of the most exciting advancements you've seen in recent years in computer vision?
So definitely the most exciting and most popular right now is in the generative AI side. So everyone probably has heard of Dolly, so where you can just give a prompt and it will generate an image from scratch just from the prompt. I think that's where things are heading nowadays, especially GANs, so generative adversarial networks, are very popular nowadays because we can use this technology to actually create more training data for us. So now our computer vision models become even stronger and even more accurate and even better.
So I want to make sure I understand what you're saying here, because in a more classical approach, we're gathering data of the real world to feed into these machines. But you're saying that now we have the ability for the machines to create that data themselves. Is that correct?
That's correct. So that actually lowers the human involvement by that much more. So now instead of having the camera or the robot in a real life scenario and we're explicitly telling it like this is what something looks like, it can essentially generate that 3D space in itself in its own simulation and kind of reward and punish itself when it doesn't do something it's supposed to do.
So this synthetic data, what are the implications of that for industry? How is that going to impact the real world deployment of these models and this technology for folks in any industry?
I think it definitely streamlines the entire process of training a new robot and a new computer vision model, because typically instead of having to bring the robot into the industrial environment or onto on site where it kind of has the same environment where it's going to be working, we can just generate that through GANs or generative AI and have it learn and work in simulation at a photorealistic environment as what it would be working in.
And maybe does it also give us the ability to simulate different types of environmental conditions? Because we're in the Blue Sky lab right now. Obviously, it's a great lab. We have lots of control over lighting conditions, and it's nice and clean. But I've been in a few manufacturing facilities that don't enjoy those same types of luxuries, right? Where you have dust flying around, and lighting variations, and lots of different things happening. So how do we use this types of synthetic data to better prepare our models for that type of real world production environment that's not as predictable as a lab environment?
So that's actually an emerging field of study and use cases right now, because there are softwares out there where you can produce this synthetic model of the environment, of the robot, of the objects you're trying to interact with. And also, it's kind of like since it's a simulated environment, you can play around with the lighting, you can play around with materials, colors, surfaces, textures, whatever you need to do in order to increase variance in, say, training data or increase variance in your reinforcement learning model. And this will all kind of help kind of bring everything in one place and make it easier for developers and engineers to deploy their models.
So this is all very interesting in an academic context, but I want to bring us back down just a little bit to real world industrial applications. What are some of the actual use cases where you would deploy these models? I can envision warehousing and logistics and kind of pick and place robotics and of course welding and painting and things like that, where you're able to recognize the object, go around it in sort of a predefined pattern. But what's the next frontier for this technology?
So if you think about it, instead of us having to program a predefined pattern, say you just drop an object in front of the robot, it doesn't know, like it's not in a predefined like a surface, or like it's not in like a set position. We can use these simulated environments and reinforcement learning as such to have the robot just figure out on its own what it's supposed to do with that object or how it's supposed to pick it up.
Because we've trained it to be goal oriented and reward or punished it over time to make sure those goals align with our goals.
That's correct. Exactly.
So, Bhargav, obviously these are very powerful pieces of technology. What sort of safeguards do we need to have in place for humans, and what considerations do folks that are developing and deploying these models need to have to make sure that things are safe and make sure that unintentional biases aren't introduced into the process?
I think a big part of that is where the human intervention part of the AI training process comes in. So if we're working with training data, we got to make sure the training data is fair and unbiased. If we're doing reinforcement learning, we got to make sure how we program or how we weigh the different rewards and different punishments are, as fair and safe as possible.
Well, this is all super interesting, Bhargav. Thank you so much for joining me and shining a light on this topic. And thank you all so much for joining us. Stay tuned. We'll have another topic for you next week on another exciting episode of Beyond the Bot.